Good morning. I am Krishna Kumar from Krishna's classroom. We will continue with our discussion on diagonalization. In fact, last thing that we did in the episode 30 of linear algebra was to prove the spectral theorem. Okay. So let us just recall what exactly we obtained. So let me state the theorem first, and then we would look at an example which will give a lot of insight into the intricacies of the computations. So let me write down what the theorem is all about. So the basic conditions are given here. I am assuming T is diagonalizable. Now we define certain invariants of spaces. That is what we did. So we had assumed it is diagonalizable. Therefore, the characteristic polynomial is of the form some lambda minus lambda 1 to the power n1 etc. Lambda minus lambda k to the power n2. So, we assume T is diagonal. T then has a characteristic polynomial. The characteristic polynomial given by where n1, n2, nk are the algebraic multiplicities of the eigenvalues lambda 1, lambda 2, etc., lambda k. Algebraic multiplicity of this is what you have, and we clearly have the degree of the polynomial. Characteristic polynomial is n, which means n1 plus this is of course irrespective of the diagonalizable. The only assumption that you need for this to be true is that the characteristic polynomial splits into linear factors. Further, from diagonalizability, T, dimension of the null space of n. In general, the dimension of, so let us, dimension of n, the null space of T minus lambda I is less than or equal to Ni, lies between 1 and Ni. Okay. So let Wi denote the null space of, for I belonging to then diagonalizability implies V can be written as direct sum of where of course the plus with a circle means that we have Wi intersection Wj 0 whenever I is different from U. And Wi's are the eigenspaces of T. So Wi is the eigenspace of T associated with the eigenvalue lambda I zero. And we have the breakup of V as W1 plus W2 etc. Each Wi invariant under that is T of so the subspaces W1, W2, Wk are invariant subspaces associated with T. Now this is an important observation. So we have successfully shown that V is the direct sum of these invariant subspaces. Now so there are k invariant subspaces, each of which is a vector eigenspace of the given operator T. Now what more do you have? Let Wi tilde denote then now let us define P from V to V defined by Pi of V equal to Wi. Here we are taking V to V which is the unique representation of V around W. Where Wi tilde is W. Therefore, Pi of this is the definition. Then Pi square equal to Pi Pj equal to 0 whenever I is different from j. These are projections. On Wi along this is true, all these statements are true for I. Then we have proved the following. I gets resolved into the sum of these projection operators. Okay, this is one statement. This is the resolution of the identity. identity. Subordinate to or related to the linear transformation. Further, B is equal to so we have a lot of nice things of structural information available on the space. The space breaks up to the direct sum of Wi's, which are invariant subspaces of T, and then you have nice projection operators Vi, and one can write the linear transformation as a linear combination of P1, P2, etc. Pk with coefficients given by lambda 1, lambda 2, etc. Now this is the beautiful, wonderful result that you have on the breakup of the linear transformation T. And in fact, now it is very transparent because it clearly tells what it does on various spaces. Because these invariant subspaces, the breakup of V to invariant subspaces means that the operation T on those subspaces do not carry the vector elsewhere. Whereas, if you take a vector which does not belong to these invariant subspaces, you cannot say where it goes. Okay, it is not visible. Which again means that you have a nice coordinate system for the vector space with respect to which T is diagonal, which in turn means that by sitting in that coordinate system and watch the operation T or watch the operator T, what it does, see that it never leaves the eigenspaces. It operates within the eigenspaces. And every vector is crafted as a linear combination of vectors in these invariant subspaces. Now this is a beautiful theorem, in fact very useful, and in fact one can, in applications, this is one of the fine result which can be used very effectively. So you have a lot of visibility now. This is the transparency I was talking about in the beginning. Okay. Why we diagonalize? I said we diagonalize because we want to make the operator look transparent. I will make some remarks while working on an example, then it will be very more clear. So these two things put in the box here, that is the resolution of the identity and the resolution of T as a linear combination of P1, P2, Pk constitute the spectral theorem. Okay, so we have now an idea of this, but maybe this is too abstract, and it will be worthwhile to look at some nice example. So let us look at an example which works according to our scheme. This example we have considered earlier. Now let me once again recall this. The example is the following. We take V to be space of all polynomials of degree less than or equal to 2 over, let B be the simplest sort of ordered basis that you normally use. Three polynomials, one the constant polynomial, the other one is simply x, polynomial of degree 1, and the polynomial of degree 2, which form a linearly independent set and spans the vector space V. Now we can define T, because you know that once it is defined on the elements of a basis, it is completely determined. Okay, so what we do is we let us prescribe that. So define T by and bx squared and extend it to the entire V by so this is T is now uniquely different. So we shall work on this T. So we are in fact going through all the things that we did until now. Okay, we are going to prove the spectral theorem for this if things work favorably. At the moment I said work favorably because put a rider that if it works favorably, because we will investigate. Okay, what happens. Then, how do we proceed? We want to get hold of the eigenvalues. To get hold of the eigenvalues, what you do is you migrate to f n cross what? Through the isomorphism. Subordinate to the ordered basis that you have. And once you do that, T takes a matrix representation. Then TB is defined as a linear transformation on T cross 1 represented by the matrix by the see the coefficients here 5, -1, 3 goes as the first column of the matrix. Minus 6, 4, 2. Three minus 6 minus 3, sorry, not 3, minus 6, 2, 2, minus 2. This is the representation. This is the representation. 5 minus 4, 3, minus 6, 4, 2. Make a mistake here. 6 minus 6 minus 6, 4 minus 6, then minus 6, 2 minus 4. Okay. That's the matrix. Now we can compute the characteristic polynomial. These are routine computations. The characteristic polynomial of is characteristic polynomial determinant of this is identity itself minus UT and turns out to be after simplification equal to lambda minus 1 So this is the characteristic. It splits up into linear factors, and 1 is an eigenvalue with multiplicity 1, or the algebraic multiplicity of 1 is 1, algebraic multiplicity of 2 is 2. Okay, so that we will keep in our mind. Now let us compute the eigenspaces. What is that? That's essentially the following. So for convenience, let me write A for so that it becomes easier to write. Okay. Now let us recall our notation. W1 is defined as, okay, come to W1, but let me just put a probably a null space of minus a. We are working in Fn cross 1. Therefore, we are writing it, and we see everything in Fn cross 1 and then translate it back. I mean, that's easy possible. So, as I was telling, that the Fn cross 1 is a copy of V. Therefore, and whatever action is going on in V, there is a corresponding action going on in Fn cross 1 and vice versa. Therefore, if you analyze what is going on in Fn cross 1, which is easier to compute, then from that you can work backwards and see what is happening in V. So that's the strategy that we use. And what is this? This is equal to the set of fold column vector x such that A of x equal to 0. Let us compute this. The rank of this is equal to 2. And in fact, you see that what is the rank of lambda I minus A equal to 2. Because let me write down that what that matrix is. That is given by so I minus A with lambda equal to 1. I minus A. So see, I minus A is this. Minus 4, 6, 6, minus 1, 1, minus 3, minus 2, then 3, minus 3, 6, now you can verify that the rank of this is equal to 2. There are two linearly independent rows that you can get out of this. Okay. Right? Therefore, rank of this is equal to 2. And the null space this is spanned by span of the vector because you know that the rank of I minus a is 2, the nullity of I minus a is equal to 1. And that's what we have computed. So bracket W1 is spanned by minus 3 minus 1 3. That is, from that you can write down what exactly is the structure of W1. Therefore we can write W1 this is 1 times I minus P. This is equal to span of we have to write down the corresponding polynomial. The corresponding polynomial is 3. I think maybe I write this properly. The right notation would be the column because we are this is the right thing. Yes. Okay. Span of the polynomial 3 minus x plus this polynomial. There is a corresponding thing that is happening in B. Similarly, is spanned by the vectors, to 0. These are the eigenvectors associated with the eigenvalue 2. Okay. What is the corresponding action that is taking place? Because if you want, you can compute and write 2y minus a is the matrix minus 3 6 6. Then 1 minus 2 minus 2, then minus 3 6, and rank of this is equal to one nullities. And that is why two vectors, two linearly independent vectors span that space. Consequently, W2, which is equal to spanned by two polynomials. What are the polynomials? 2 plus x and 2 plus that's corresponding to this, you get 2 plus x. Corresponding to this, you will get 2 plus 0 times x plus 1 times x square. 2 plus x square. So this is the story how W2 looks like in the polynomial space. Now we observe the form. Now what we do is we choose an ordered basis B prime, which is constituted by the eigen functions. They are 3 minus x square then 2 plus x 2 plus x square. But then quickly check that these three vectors are linearly independent, and it forms a basis for the polynomial space. They are polynomials of degree less than or equal to 2, and they span the whole space, the linearly independent. Okay. Observe P of P of this is equal to 2 times, this is very easy to compute, P of what is it, 2 plus x square equal to 2 times, that means 3 minus x plus 3x square is an eigenvector of t corresponding to the eigenvalue 1. 2 plus x is an eigenvector corresponding to the eigenvalue 2. 2 plus x square is also an eigenvector corresponding to the eigenvalue 2. So this is what it is. Now let us write down this. What is this? See, if you write write this in terms of the ordered basis. You see that is 1 times 3 minus x plus 3x square plus 0 times 2 plus x plus 0 times 2 plus x square. Okay, therefore the first column of the representing matrix is going to be 1, 0, 0. The second, similarly for t of 2 plus x equal to 2 times 2 plus x, which can be again written up in terms of this ordered basis, which will give you this is time. So we have successfully diagonalized the problem in this case. Okay. Now what we are interested in is to go beyond this and then talk about all these projections, etc., and how the projections look like, and how do they add up to give you the identity operator, and how the linear combination of them with coefficients as the eigenvalues rework your linear transformation. That's what we are. So let us work it out in Fn cross and then work with it. Then come back to this. So to understand, okay, so what is P1? P1 is from W1 to P1 is the projection. P2 is from P2 so let us write down what this P1, P2 are. Okay, this is the general scenario. So what we are working is P1 from one to the space spanned by, so let me write this, and then P2 from so W2 we have written out what exactly it is. W2 is a span of this, W1 is this, therefore, see, you see that W1 so what you have is this. What is this one? these vectors. We will work it out. Okay, so let us work out something. So what we do is, if you want to express P1, what one does is, we have to say what it does on each of these of the elements of the vector space, because our description is in terms of the basic space, because in this representation it is very easy. With B prime it is very easy what these operators are. I will make a remark about this. So our discussion will be for B equivalently with respect to the basis B1 1 0 0 0 1 0 and 0 0 1. The corresponding order is for okay, let's move it. What are the computational things that we have to make? So what do we have to do? We have to look at this P1 and P2, or equivalently P1 and this P1 and P2. So we will work it with Fn cross 1, which is easier to handle, and then translate it back to B. So let us do that. So what do we have to do? So the operator to get the matrix representation for P1, what one does is you have to say these things. What is this? You have to say P1, how it acts on zero. Okay. And to get hold of this, what is this? So what one does is you write 1 0 0 in terms of the order basis for W1 and W2. Okay, so you can write, this is easy to compute, this is equal to -1. I leave the computation to you. These are trivial computations. 3 -1 3 plus -1 2 plus 3 2 0 1. You can check this quickly. I'll check this for you. Minus 3 minus 5 plus 6 will give you 1. 1 minus 1 is 0. Then minus 3 plus 3 is 0. So it checks that. This is a unique breakup along these vectors. So this is the component on W1. This is the component on W2. So just like that. Okay. I'll just do it for P1 and then for P2 and P3 you go through the computations. That's a good exercise. But that will allow you to understand what it is. Now what exactly is this? So the P1 of 1 0 0 is actually the projection is onto this. So if you break it up on this, it should give only this element. So this should be defined as minus 3 1 okay. This is the transformation. And similarly, one can work out 0 1 0 is given by 2 times 3 minus 1 3 plus 3 times 0 and minus 6 times you can quickly check. This is 6 plus 6 12 minus 12 it is 0 minus 2 plus 3 that is 1 and minus and 6 minus 6 that is 0. So this is the correct resolution of this one. Therefore you have P1 of 0 1 0 is again it has to go to this. Therefore it should be equal to what is it? 6 minus 2 6. Okay. Similarly, you have P3. Sorry. Similarly, you have what is it? Is written as 1 times 3 minus 1 3 then 1 times 2 1 0 and minus 2 times 2 0. And from this we have P1 of this is 0 0 1. This again you can check quickly. Minus 3 plus 2 minus 2 3 minus 9 plus C1 equal to 1, so 3 sorry, this is wrong. I rewrite this. This is 2 into a mistake. Sorry, let me correct it. Sorry. Now we see. This is 6 plus 4 minus 10 0 minus 2 2, that is again 0, 6 minus 5 1. So that's right to break up. Therefore P1 of 0 0 1 is in fact we can write down the matrix of T, therefore which implies this will be in fact P1 of this is equal to minus 3 1 minus 3 1 minus 3. So minus 3. Okay, right. So there's a minus sign missing there. And that gives you the first column of the matrix as minus 3, 1, minus 3. Then, what about this? This is equal to 6 minus 2, 6 minus 2, 6, and then 6 minus 2, 6. And you can see that the rank of this matrix is actually 2. The nullity is, the rank of this matrix is 1. Therefore, the nullity is 2. Therefore, the null space of P1 has dimension 2. Okay? Right. Now one can check this. Flex of protection. I leave that to you to completely verify that. Similarly, we can work out P2. P2 is on W2. Now you see W2 is spanned by 1 0 0 and 0 1 0. span of what vectors is actually 2, 1, 0. This is the span of this. Each eigenvector is associated with the eigenvalue. Therefore, now what is P2? P2 is the projection order. So P2 of this is equal to the following. Now you recall what is the map that you have. So let me just write here 1, 0, 0 is resolved into minus 3, minus 1, 3, then minus 2, 1, 0, and plus 3. This is the resolution. Therefore, P2 of this will be essentially this vector. Okay, that's the copper vector. Therefore, this is equal to minus 2, 1, 0 plus 3 times what is called 2, 0, 1. That is equal to minus 2 plus 6, 4, 1. This 4, 1, 3. Okay, let's see what it is. This is equal to, oh sorry, I wrote down here minus of this. This is minus of this. Therefore, this is equal to 4 minus 1. Correct. Similarly, this I write as this is actually the sum of these two. Okay, and that you can write. It will be 6, 12 minus 12, so minus 6. So this is equal to, in fact, minus 6 or if you want I can write 3 times 2, 1, 0 minus 6 times 2, 0, 1, which is equal to, I can give this as minus 6 correct. And P2 of 0, 0, 1 works out to be simply this part. 2 times 2 and 0 and that turns out to be simply minus 6, 2, minus 6, 2, minus This is correct. Therefore, the matrix of like this, right? The matrix of P2 given by 4 minus 1 3, then that is the matrix representation for P2. Okay. Similarly, we will write P3. Okay, P2 is that. Now we can write down what exactly are the corresponding polynomials. So one observes that the following holds. This is equal to, what do you have? Correspondingly, you write down these two matrices. This is the matrix for P1 and this is the matrix for P2. Minus 3, 6, 6. 1, minus 2, minus 2. Minus 3, 6. Plus 4 minus 6 minus 6. Minus 1, 3, 2. Then 3 minus 6 minus 1. So you just add up. If you add up, what do you get? This will turn out to be simply 1, 0, 0, 0, 1, 0, 0, 0, 1, which is the identity matrix. This is the identity matrix. Okay. Similarly, let us compute the following. Okay, we will compute this. This is equal to minus 3, 6, 6, minus 1, minus 2, minus 2, minus 3, 6. Two times that is 8 minus 12 minus 2. Then you have minus 2, 6, 4, 6 minus 12 minus 10. Okay, that is 2 times this particular matrix, which Let us work out. Add up these two. If you add up these three, then you will get 5 minus 3 plus 8 is 5 minus 6 minus 6 minus 1 4 2 minus 3, so you get 3 here, minus 6 okay. Now, which is essentially the matrix representation for okay. So we have essentially written down the spectral theorem for whatever is happening in Fn cross 1. So the spectral theorem is valid. Because these two statements are I equal to, this is the identity operator which is the same in all in Fn cross 1. This is equal to P1 P2, that is the sum of the observations, and then you have 1 times plus 2 times. See, this is the eigenvalue lambda 1, this is the eigenvalue lambda. Therefore, this is the verification of the spectral theorem for dB. Now, what about the corresponding result for P? Okay. Try to translate this whole thing to what you call the space V. Okay. So let me write down P1. Okay. So the matrix for P1 is this, which means we have P1 of 1, this is equal to minus 3 plus x plus square. P1 of x equal to 6 minus 2x plus 6x square. P3 of x square equal 6 minus 2x plus 6x squared. Okay. So this is the map that defines P1. Okay. Now P2 is then defined by this is definition of P1. P2 of 1 equal to four minus x P2 of x equal to what? Minus 6 plus 3x minus 6x squared. P2 of x squared equal to minus 6 plus 2x minus now let us check what happens to P1 plus P2 of 1. So P1 plus P2 of 1 this is equal to, see, you are adding these two. When you add these two, you will end up with 0. Because they cancel out. P1 plus P2 of this is equal to, you see that P1x is 6 minus 2x plus 6x squared. This is minus 2x this will be x minus 2x plus 3x is x, and these two cancel. And P1 plus P2 of x squared, this is equal to, compute this, 6 plus minus x is 0, 2x minus plus 2x minus 2x is 0, minus 5x square plus 6x square, so this is x square. So P1 plus P2 has the property that it maps 1 to 1, x to x, and x square to x square. Therefore, which implies P1 plus P2 equal to the identity of x. That is the solution of the identity. Okay? So it's the right interpretation. Now what about the so you see, you compute this. Now this of x of 1, this is equal to 5 minus 3 plus x minus 3x square plus 8 minus 2x plus 6x square, and this turns out to be simply 5 minus x dx. Then similarly, p1 plus 2p2 of x, this is equal to, in fact you can work out from here, the second column which is lovely now. 6 minus 2x, this is this one, plus 6x square plus minus 12 plus 6x minus 12 square, and that turns out to be simply minus 6 plus 4x minus 6. Now we will write down what exactly is this. It is E1 this we write as 6 minus 2x plus 6x square plus minus 12 plus 4x minus 10 square, and that gives the computation that, if you simplify, is going to be equal to minus 6 plus 2x now let us check with what we have started with. We have started with the definition of P. Now definition of P is this. Recall P of 1 equal to 5 minus x plus x square, this is the one. Px equal to minus 6 plus 4x minus 6x square, and P of x square equal to minus 6 plus 2x minus 4x square, and that implies equal to P1 plus practice is saying 1 into P1 plus 2 P2. Therefore, the spectral theorem or that is what you get is this I equal to 1 P1 plus P2 and P equal to 1 times P1 plus 2 times P2. This completes our verification. Or I think you should be fairly well convinced that this is so. And I think the best way is to take another example and then start computing. It takes some time, but probably gives you a lot of insight and lot of clarity to what all things we have been saying all these days, going to the matrix representation, going for the representative space, working on the spectral theorem here. There is the analog of this happening. So, now I think you should be fairly convinced that the going to the matrices, diagonalizing it, and then pulling back is ideal. Now, see, one of the things that you observe is this. That is, with the Eigen functions. Okay. See, here the description had been based on 1x squared. But suppose we redraft the whole thing, and what happens with equal to, what is the basis that we have chosen? 3 minus x 3x square 2 plus x 2 plus x square. Suppose we choose this basis, then we have found that P of that means this is an eigenfunction of t belonging to the eigenvalue 1. Similarly, so W2 is spanned by these two vectors, and in fact you can choose another basis there. That's quite possible. Okay, so there is no reason why you should choose only 2 plus x and 2 plus x squared. So that seems to be the simple choice because you get 1 0. One of the entries has zeros. That's the reason we have chosen it. But you can choose some other set of vectors and then compute everything, and everything will work out with this. Okay, therefore what you have? In this scenario, what you have is this. Okay. What is P1? P1 turns out to be simply, what we have is this. This is P1. Okay. That means P1 of is taken as 3 minus x plus 3x square. P1 of that's the choice. What about P2? P2 is chosen as P2 is defined by square. Okay, so this is about P, this is about P1, and this is about P2. Now you observe that equal to P1 plus P2 of what does this mean? This means P1 plus similarly you verify this. Okay. Similarly you verify that P1 of P1 plus this is this. Which implies P1 plus so the spectral theorem is verified in another basis with reference to another basis. Okay, so we first did it with respect to the basis B, and now we have verified it with with respect to the basis, ordered basis, B prime. The advantage of working with B prime is that, see, if you go for the matrix representation of I for P1 and P2, see, the matrix representation P1 B prime is 1. The matrix representation for P2 is essentially 0, 0, 0, 0, 1, 0, 0 for diagonal. Okay. Similarly, you compute this one. What is the matrix representation for P1 plus 2 P2? Or P1 plus B prime, this is equal to 1, 2, this is the diagonalization. So in both these cases, the structural part of the spectral theorem is very familiar, and that's one of the great theories. Okay. So that leaves us with a question. The basic question that we are going to address now is this: is every T diagonalizable? We have had examples to show that possibly no. Okay. Then, in such cases, what do? Do you have a similar type of theory that you can develop? In fact, it leads me to the heavy use of what is called polynomial theory. I have kept the use of polynomial theory to almost negligible level, except I have just said that the characteristic polynomial is brought into the picture and nothing more. And this is the important thing to observe. I have not brought in the polynomial theory so far. But now you have come to a stage where it is certainly advantageous to make use of the polynomial theory. And this is where we go from this stage. Thank you very much.